Hello everyone. In this video, I am going to explain two-dimensional Fourier transform, which is a topic from digital image processing. Now, before starting or going towards the topic, let's understand what is meaning of transform and why it is necessary, why it is required. So, if you take informally for a layman, transformation is any way of changing something. Suppose I want to change something, that means I want to transform it. Even if we change the style of clothing, then we say that it is a transformation. So transformation means way of changing something. Now let's take one example. Suppose this is a graph in which this is x-axis and this is y-axis, say. Now suppose we want to plot a 2, 3 on the graph paper. That means value of x is equals to 2 and y is equals to 3. So it is very easy to plot it on the graph paper. We know we will take this x is equals to 2, y equal to 3 and we will plot this point here, that is point A. Now let's take another example. Suppose I want to plot a is equals to infinity comma infinity. That means now x is equals to infinity and y is also equal to infinity. Now this is not possible to do or plot it at least on the notebook or wherever it is possible to plot. So what is the solution over this? Now I want to plot a is equals to infinity comma infinity. I cannot reject it. So there must be some solution over this. So what I can do is I will take any variable z. I will write z is equals to 1 by a, and then instead of plotting a, now I will plot z, because now since a is equals to infinity, my z is equals to 0, and now it becomes very easy for me to plot z equal to 0. So I can plot it here. This is known as transformation. What is this? Z equal to 1 by a is known as transformation. This is the simplest form of transformation. So what does transformation mean? In mathematics, transformation are often used to move an object from place. Move an object from place where it is hard to work with. Means if somewhere with some object, if it is very hard to work with, then we have to move it to some other place where it is simple. That means if you have some complex mathematical operation at one place, then what you can do is you can transform it into simple form, solve it there, and then again go back to main phase. So for some people, moving the object is equivalent to choosing a new way to view the object. We are not changing the object. We are not changing the value of the object. Just we are changing the view of object. Okay, so understand, transformation is just a way of changing something wherein we don't change the value of original object. So what is Fourier transform then? Fourier transform, we know that everybody knows this definition, convert time domain signal into frequency domain signal. That's right. But what is the difference between time domain signal and frequency domain signal? Now let's take an example. Suppose we have this time domain waveform. This is a sinusoidal waveform on which on x-axis there is time, on y-axis there is amplitude. So we have a sinusoidal waveform with frequency 4 Hz. Now we want to represent it in the frequency domain. How to represent in frequency domain? In frequency domain signal, on x-axis there will be frequency and not time. So here there was a time on the x-axis. So in sinusoidal signal, as you know that the amplitude varies continuously with time. So signal waveform is like this. Now we want to represent same in a frequency domain. So on x-axis there will be frequency and y-axis same magnitude. So what we can do is, now it is 4 Hz. So how to represent it? Suppose we know that this is the frequency of the signal is 4 Hz. So we can represent it like this. 4 Hz of this particular amplitude. Now let's have another waveform. Suppose now we have another waveform with higher frequency. Higher frequency means 12 Hz frequency. You can easily see that the frequency of this signal is greater. Now we want to represent this waveform in frequency domain. Again simple, on x-axis take frequency, on y-axis amplitude, and then this is your frequency domain signal for this waveform. So this is known as time domain signal, and these signals are known as frequency domain signal. What Fourier transform does, it converts time domain signal into frequency domain. Why? Because it is very easy to represent and understand in frequency domain than to work in time domain. Now let's take example. As we said, we have one waveform with frequency 4 Hz. We have another waveform with frequency 12 Hz. Now let's add these two signals in time domain. When we add these two signals in time domain, it will be represented something like that. So what is this? This is a signal which is the addition of two sinusoidal waveforms having frequency 4 Hz and 12 Hz. So it will look something like this. Now since we have added them, we know that the frequency is 4 Hz and 12 Hz, and hence it is very easy to represent it in frequency domain. Like here we will draw 4 Hz and here we will draw 12 Hz. So this is frequency domain representation of this signal, this is frequency domain representation of this signal, and this is frequency domain representation of this addition of two signals. Now let's take another example. Now suppose we have three waveforms. This is one sinusoidal waveform, this is another frequency, and this is another frequency. Everywhere the amplitude is different. So when we add these kind of sinusoidal signals together, we will get something like that, which is kind of a random signal. Random signal. Now suppose let's take an example that we have this signal. Now we have this signal, and now we want to find out that original sinusoidal signals. That means we want to find out the original sinusoidal signal after adding we got this. So what we have to do for this, for that purpose, we have to take Fourier transform of this signal. When we take Fourier transform of this signal, we will get this signal back. So this is an application of Fourier transform. Now what is inverse Fourier transform of signal? Then the inverse Fourier transform is simple. Fourier transform means converting time domain signal into frequency domain signal. And inverse Fourier transform means converting frequency domain signal back again in time domain. So what is inverse Fourier transform? Convert signal from frequency domain to time domain. That means if we have this signal, then converting it back into time domain signal is known as inverse Fourier transform. Remember that whenever we take a transform, it is always required that we go back to the original domain. Okay, because why do we take transform? To make things easy, to make mathematical calculations easy. But once we perform the calculations, once we complete the calculations in another domain, again it is necessary that we go back to the original domain. Now Fourier transform of, it was all about, the previous explanation was all about Fourier transform and inverse Fourier transform of signal. Now Fourier transform of image. All of us know that image is two-dimensional signal. Image is two-dimensional signal. The Fourier transform is an important image processing tool. It is a tool which is used for decompose image into its sine and cosine components. So what Fourier transform of an image does, it decomposes, it divides the image into sine and cosine components. As we are only concerned with the digital images, as we are talking about digital images, we will restrict the discussion with the discrete Fourier transform, that is DFT. Now, what is the formula for DFT? For a square image means n by n image. N by n image means there are n columns and n rows. Suppose we have this image, there are n columns of pixels and n rows of pixels. So n by n image, the two-dimensional DFT, two-dimensional discrete Fourier transform is given by this formula. What is this? F u comma v, it represents discrete Fourier transform of image. What is f of x comma y? F of x comma y is original image. What is this e raised to power minus j2 pi xu by n plus vy by n. This is known as basis function. So what is the form of this? The form of this is e raised to power j theta. What is value of e raised to power j theta? E raised to power j theta, we write it like cos theta plus j sin theta. And if it is e raised to power minus j theta, that means it is cos theta minus j sin theta. So what is value of this? It is a function, it is a basis function, consists of cos terms and sine terms. What is e raised to power minus j 2 pi xu by n plus vy by n? It is consists of cos terms and sine terms. Now in this equation it is written f of x comma y is input image. This input image is spatial domain. This exponential term is a basis function. This term, as I explained you already, this term, exponential term, is a basis function. What is meaning of basis function? According to the value of this basis function, the value of this Fourier transform will change. The basis functions are sine and cosine waves. The basis functions are sine and cosine waves. Why? Why? Because it is in the form of e raised to power minus j, and this is nothing but theta. It is in the form of e raised to power minus j theta. That means it is cos theta minus j sin theta, and that's why the basis functions are sine and cosine waves with increasing frequencies. Now, inverse Fourier transform of image. As there was inverse Fourier transform, in inverse Fourier transform, we convert signal from frequency domain to time domain. Similarly, that means for signal from frequency domain to time domain. Similarly, for images also, we can convert it from frequency domain to time domain. So, Fourier images can be retransformed into spatial domain. So the inverse Fourier transform is given by equation. This is the equation of inverse Fourier transform. F of x comma y means it is an equation of original image 1 upon n square. What is n? N is number of rows and number of columns, columns, pixel, rows of an image. F of u comma v is nothing but actual Fourier transformed image, because we are calculating inverse, so it is Fourier transformed image. And this is basis function. Remember that here there is no minus sign, but this is a basis function, same form e raised to power j theta. Now, what information Fourier transform of image gives? What exactly we extract while calculating Fourier transform of an image? Very important concept. The response of Fourier transform to periodic pattern in spatial domain images can be seen very easily in the following artificial images. What is meaning of this? Or what exactly Fourier transform interpret? Fourier transform gives us the variations in black and white patterns. What exact information we get from Fourier transform? Variations. How many variations are there in a particular path, in a particular direction, in black and white patterns. Now let's consider this image. Now in this image, if you go this side to this side, if I go from this side to this side, there is no variation in the color. If we consider this, it is completely white from this end to this end. If I go from here to here, it is completely white from this end to this end. If I go from here, it is here to here in this direction, it is completely gray from this end to this end. That means if we go from this end to this end, there is no variation. There is no variation in black and white patterns. Instead, if you go horizontally, let me erase it. Now, if you go in this direction, you can see that here you have started with the white color, then here it was gray, then here it is black, then again here it is gray, then again here it is white and black and white and so on. So if you go in this direction, the variations are more. And when we take the Fourier transform of this image, you will get these horizontal pixels. like this, it indicating that the variations in black and white patterns are in this direction or in this direction, like this. Okay. Instead, if you take this image, if you go in this direction, there is no variation. But if you go in this direction, there are more variations in black. Everywhere it is, here it is black, then again white, then again black and white, and black and white is changing. So if you take Fourier transform of this image, you will get this pattern. So what it indicates, it indicates that there are more variations in black and white patterns in this direction. Instead, if you take this image, you can see that there are variations in this direction also and this direction also, and hence the Fourier transform of this image will be something like this. It is showing variation in this direction as well as variation in this direction. Again, let's take an example. Same image we have here. Since the variations are more in this direction, so Fourier transform of this image will be something like this. If we take this image, this is a text, that means written script, and since it is a written script, the variations are more in this direction because there is this black line, and then here it was white, and then again white, and then again written text, then again white, and then again written text. So variation is more in this direction, and hence we take Fourier transform, we will get something like this. Now rotate this image. If we take the Fourier transform of rotated image, the Fourier transform will also rotate. So this is one of the property of Fourier transform. It is said that when you rotate the image, the Fourier transform will also rotate because the variations in white and black spec pattern will also rotate. Now let's solve one example. What is the example? Calculate two-dimensional discrete Fourier transform of 4x4 grayscale image. So it is mentioned it is a grayscale image, 4x4 image, that means there are 4 columns and 4 rows. It is represented by f of x comma y. How to solve? How to calculate two-dimensional discrete Fourier transform of this image? I will give you directly solution, no derivation. I explain in this particular video. So here it is a very simple formula, f of u comma v, f of u comma v is Fourier transform of this image. It is always represented by capital F and image is represented by small f. It is equals to kernel into f of x comma y. What is f of x comma y? It is original image. And here you have to take transpose of kernel, kernel transpose. So what is kernel? Kernel is nothing but it is given by, it is a basis function. Kernel is DFT basis function and it is given by, for n is equals to 4. That means for 4x4 image, the kernel is given as like this and it is fixed. If image is 4x4, the kernel is fixed. It is not going to change. So how to solve this? Very simple. You know this formula, kernel into f of x comma y into transpose of kernel. This is nothing but matrix. This is matrix. Okay. So take this kernel, write out here, then take image f of x comma y and then again multiply transpose. Here it is transpose, so it is same. Transpose of this is this and it will both are same because their rows and columns are same, so it will not make any change. Now what you have to do, you have to multiply these two matrix and you will get some value after multiplication. Then write this matrix. For this you should know the matrix calculation. Okay, otherwise you will not be able to solve this problem. After multiplying these two, you will get this, then multiply this with this kernel and you will get the final value, that is 16 in the corner. So what we did, we had image f of x comma y, we have taken two-dimensional discrete Fourier transform of grayscale image and we have got this. So if you observe this image, what is the kind of image it is? It is 0, 0, 0. 0 represents black pixels and this value represents white pixels. So you will get white at this particular corner and all over in the image it will be black. So it was all about Fourier transform and how to solve the problem on Fourier transform. In the coming videos, I will come back with the more complex problems on Fourier transform. I hope you understood. Thank you very much. Thanks for watching.